Have you ever just looked up and wondered what's happening way, way up there? Today, we're going on a journey, climbing through the invisible layers of our atmosphere to explore the shield that keeps us all safe from the harshness of space. It's a system that's incredibly complex, always in motion, and absolutely essential for life. Okay, let's dive into this. When you see a picture of Earth from space like this one, what you're really looking at is that thin, fragile-looking blue line. That gaseous envelope is everything. It's our planet's first and last line of defense, and we're about to see just how it works. So what is this shield really? Well, it's not just one thing. Think of it as a multi-layered system powered by the sun and literally anchored to the planet by its own gravity. To get our heads around it, we're going to climb up through it, layer by layer, starting with the one force that holds it all together. So first things first, what's to stop all our air from just, floating away into space? The answer is a force that you feel every single second of your life, but you probably don't think about it in this context. That force, of course, is gravity. It's the anchor for this entire atmospheric system. Now, Earth's gravity isn't quite strong enough to stop a tiny bit from escaping over eons, but it is absolutely crucial for keeping the overwhelming majority of our atmosphere right where we need it. And what's so amazing is that the very same laws of physics that keep our planet orbiting the sun are what hold the air you're breathing right now close to the ground. It's this fundamental constant that makes everything else we're about to explore even possible. Okay, so with our feet planted firmly on the ground, thanks to gravity, let's start our climb. We're going to move up from the surface, right through the different atmospheric layers, and you're going to see how things change, and fast. Now this chart, this is basically our map for the whole trip. Just look at those curves. You can see pressure and density just plummet as we go higher. But the temperature line, it does this wild zigzag. And every single twist and turn in that line tells us we've entered a new layer with a totally new job to do. And the thing is, these first few layers are all about direct protection for us down here. We start in the troposphere, that's home base, where all our weather is. Above that, you've got the stratosphere, with that all-important ozone layer soaking up the sun's worst UV rays. And even higher up, the mesosphere acts like a cosmic shooting gallery, burning up most meteors before they ever get close. Just let that sink in for a second. Only 30 kilometers up, that's less than the distance of a marathon, and the air pressure is already 100 times lower. The air gets incredibly thin, incredibly fast, and it's in this thinning air that something almost like magic starts to happen. As we get up into this near vacuum, we're entering a zone where the sun's energy isn't being filtered anymore. Up here, the raw power of solar radiation is so intense that it literally starts ripping atoms apart. You've got these incredibly high-energy photons, extreme ultraviolet light and X-rays, just streaming from the sun. They travel 93 million miles, and this is where their journey ends, in a pretty violent collision with the few atoms that are left in our upper atmosphere. This whole process is called photoionization, and it's how the ionosphere gets made. Basically, a solar photon hits a neutral gas atom with so much force that it knocks an electron clean off. What's left behind is a positively charged atom, we call that an ion, and a free-floating electron. This soup of charged particles is a whole other state of matter called plasma. Yeah, this is not a gentle process. It's a high-energy bombardment. It's so intense that, as the source material puts it, these photons can strip molecules and atoms of one or more of their electrons. This completely transforms the nature of our upper atmosphere, creating this incredible electrified shell around the entire planet. But here's the cool part. This electrified shell isn't just one big, uniform blob. It's actually a series of distinct regions. We call them the D, E, and F layers. And each one has a very different and very useful effect on something we use every single day, radio waves. You can actually see how this structure gets built right here. This chart shows how different kinds of solar energy make it to different depths. See the separate peaks? The most powerful radiation gets absorbed way up high, while the less energetic stuff makes it deeper, creating this beautifully layered structure of different ions. So what's the practical upshot of all this? Well, the lowest layer, the D region, actually absorbs AM radio waves. That's why your car radio can sound weak during the day. But the highest layer, the F region, acts like a giant mirror in the sky. At night, it can bounce those AM signals right back to Earth, letting you pick up radio stations from hundreds, sometimes even thousands of miles away. So why does this cool radio trick only work at night? Well, it's because that D region, the layer that absorbs the radio waves, is created by direct sunlight. When the sun goes down, the D region basically vanishes. And that clears the way for radio signals to shoot all the way up to the F region, bounce off that cosmic mirror, and come back down on the other side of the planet. And with that, we've reached the very top of our climb. This is the exosphere. It's the final, thinnest layer where our atmosphere just sort of fades away into the vacuum of space. There's no hard line here. It's just a slow, particle-by-particle transition into the void. So what does it take to actually leave for good? To break free from Earth's gravity completely, a particle has to hit this speed, 11.2 kilometers per second. That is Earth's escape velocity, and it is a ridiculously high bar to clear. This chart shows us the typical speeds of different gas particles way up at the top. The heavier guys, like oxygen, they're way too slow. But look over at hydrogen. A few of the fastest-moving hydrogen atoms can actually reach escape velocity. This means our atmosphere is constantly, though very, very slowly, leaking its lightest elements out into space. Now, this process is incredibly slow and stable, so there's nothing to worry about. But it is a powerful reminder that our atmosphere isn't just some static blanket. It's a dynamic system, caught in a constant tug-of-war between the gravity that's pulling it in and the sun's energy that's trying to blast it away. And that leaves us with a final thought to chew on. This invisible shield, the ionosphere, is our planet's dynamic front line, its interface with the cosmos. It's being shaped every single second by the sun. So as our star goes through its own changes and our planet continues to evolve, the really big question is, how will this critical, invisible shield respond?